Hello, today we are going to learn more about how we can do some further analysis in the improve phase of Six Sigma. More specifically, we are going to take a look at this problem where we have information of a company and then they listed their data. For example, here we do have in the C column total employee hours that they put into during a shift, whether it's a day shift or night shift. And then we also know for that specific shift, the total number of customers that they served. And this column E stores the overhead cost that they observed during these shifts, okay? And here, column A gives us the time period. This can be a day. This can be portion of the day. Let's assume that this is just continuously increasing and has nothing to do with our data. Just indicate the timestamp of these three information as an input, and that produce this overhead as an output. So today we're going to take a deeper look into multiple linear regression, and it is going to help us understand how we can predict a response variable. In this example, it is going to be the overhead cost based on our process input variables. So our process input variables in this exercise is going to be which shift of the day, like it is a night shift or day shift, and the total employee hours the company put in to serve these many customers, and eventually they observed this much overhead, right? And we do have data for 36 different shifts. And what else we have? After we run multiple linear regression, we are going to identify the importance factors of these input variables. And by using that information, we are going to try to predict for the future, right? So as the data continues, let's assume that we are planning for the future, let's say next week or next month, whatever that is. And let's assume that we know that the shift is going to be day or night. And we assume that we plan to have this many employee hours that we are going to put into the service on that shift. And with this many number of customers that we expect to serve, let's assume that by learning from the multiple linear regression, can we predict the overhead cost here? Multiple linear regression hopefully is going to give us that prediction power. So it's going to do two things for us. Number one is it's going to identify if these input variables are significant in predicting this overhead cost. If those are significant, what would be the importance factors that we can use to put together an equation, hopefully, to predict the overhead cost. And then at the final step, we are going to run that prediction to decide the overhead cost for the future. Okay, so let's get started. I already opened up a Minitab page for this work. And as we always do, let's copy our data set into Minitab. Okay. Right, I hit copy and now paste. All right, perfect. So our input data is already in Minitab. Let me expand these columns so that I can read the names correctly. All right, we do have all the information that we have here. So if you would like to do regression analysis, you just need to go to stat, and then regression is on the second spot from the top. And then you just need to go to fit regression model. Okay, there are a couple of key things that I would like to go over here. Responses, you can put multiple responses here, but that's out of topic. We are going to only work with a one response variable. In this case, this is our overhead cost. It is the variable that we're trying to predict. Okay, so in many different examples, in many different applications, this might be something else, but make sure that you put the variable that you're trying to predict here as a response variable. There are multiple jargons people use. So for example, some other people call this dependent variable. We call it response variable. We're going to adopt the use of Minitab's language here, right? But if you hear like the response or dependent variable or predicted variable, make sure that those are all referring to the same information, right? And then there are two input categories that we can put in. The first one is continuous predictors, and the other one is categorical predictors. Now, it is really important to identify the difference between these two. So let's take a good look at our input variables. We do have the shift variable here, right? It is going to tell us whether it's a day shift or a night shift. And we do have some numerical variable, numerical observations for the total employee hours and total number of customers here. It looks like the total number of customers is changing between 20s to 30s, maybe even 40s. We have even 50 we have here, right? So this is a numerical observation and it is a continuous variable, right? And then total employee hours, again, it is in terms of hours, it is measured in continuous scale. On the other hand, shift variable can take up only two observations, right? It is either a night shift or a day shift. So shift variable here is a categorical variable, right? Usually when you have, for example, information on your employees like gender type, female, male, or other categories, those are good indication that you are dealing with categorical variables. Or for example, demographics or race or the state information, usually like those information that has multiple categories or limited number of observations that can be put in there is going to be your categorical variable. So it is important to identify between categorical variables and continuous variables because it's going to change the way that Minitab is implementing multiple linear regression on them. Or any other software. If you're doing this in Excel, it is going to be also important to decode those categorical variables into numerical ones. Minitab does that automatically. You don't have to do anything extra. Another good example of categorical variable is weather type, for example, rainy, stormy, snowy, sunny. So you can just attribute a numerical variable for those. If you're doing this in Excel, you would have to do that. But if you're doing this in Minitab, you don't really need to. That's the beauty of using the software. So let's get back to our example. So I was on Minitab, yeah, and I clicked on stat, regression and fit regression model. Now I know that I do have categorical variable or predictor as my shift. Let me select first the overhead as my response variable. My continuous predictors, I am not going to include the time because it's not going to be, well, in some other implementations, it might be important, but in this one, I'm going to exclude it from my analysis. So I'm going to use my total employee hours as my continuous predictors, total number of customers, and my categorical predictors is going to be only one column. That's going to be the shift. Let's click on these options to see what we have. We are not going to touch this, but if you are interested in, for example, studying the impact of total employee hours and total number of customers or shift, you can just cross them each other here with these settings and then get that. For this implementation, I'm not going to do that. If I go to options, so you can get to select your confidence level, level of significance here. We're not going to touch those. Coding, this is important because we do have one categorical predictor. Well, Minitab already identified that. And it is going to tell us that it's going to decode it as 1 or 0. And it's going to take day as a reference variable. So If shift is a day, it's going to call it 0. And if it is a night, it's going to call it as 1. Okay, this is how it works. Stepwise linear regression, I'm going to explain it later. Validation, we don't really need that. Let's check out graphs. I like to see graphs. I click on Pareto and I click on to see those validation graphs in one. And I go to results. Yeah, I want to see all those. And that's it. And you click OK. Minitab runs multiple linear regression analysis for you, and it produces lots of useful stuff here. So let me get onto those information. Let me get this out of the way. So first and foremost, it is telling me that it decoded my categorical variable shift into 2, 1, and 0. I explained it earlier. 0 means day and 1 means night. And it produced two different prediction equation for me. If it is a day shift, it tells me to use this first equation. Overhead is equal to this constant plus 43.38 times total employee hours plus 773.9 times total number of customers. And if it is a night shift, it is encouraging me to use this equation, right? As you noticed, the coefficients of total number of customers and total employee hours are not changing here and here. Those are the same. Only the intercept is changing. This constant is changing. You could actually use just one simple equation and then put in that equation 1 as a coefficient for night and 0 for day. But Minitab, brings things into pieces, breaks things into pieces, and it is helping us to identify if it is a day shift, use this equation, if it's a night shift, use this equation. So what we can see here is the overhead cost is increasing if I'm increasing my total employee hours, if it is a day shift, right? Or night shift, it doesn't matter. Well, night shift comes with more overhead costs because the intercept, the coefficient is already 5,270 versus a day shift, which is 3,959. And all others are the same. So from these two equations, I can already conclude that my night shifts overhead is going to be much more expensive, regardless of my total employee hours and total number of customers, because see the difference between these two intercepts are going to be because of the night shift that I'm offering, right? And let's see what else we can conclude here. We see no minus signs here, and here. So it means that if I increase total employee hours and total number of customers, my overhead is going to increase in both day shift and night shift. How much they are going to increase, or the overhead cost is going to increase. Well, if I increase the total employee hours by 1, it's going to cost me $43.38 because this is the coefficient here, right? If I increase, if I serve one more total number of customers, then my overhead cost is going to increase by $873.90. Okay, so these are the two regression equations. If you don't have any categorical variable, you will only get one regression equation, okay? This coefficients table is very important, and it is basically telling you these coefficients here that you saw in this equation. So those are sorted in coefficient here, right there. And one thing to realize here is that this coefficient constant for the constant or for the intercept term here, right? This 3,959 can be seen in the day column because day is the reference variable. And what it does is for the night equation, it adds the night's coefficient here to this coefficient, which is going to be identical to 5,270. And writes the same equation with the other two variables. As you can see, 43.38 is the coefficient here for the total employee hours, and you can see it in the equation. and 873.9 as the coefficient of the total number of customers. You don't need to worry about SE, coefficient, t-value, t-statistic value here, but what we need to know is the meaning of the p-value and VIF. Usually we look at the p-value for the predictor variables or independent variables, or the variables that we believe we took as an input to predict the alpha, right? So let's check how total employee hours, the p-value is 0. Total number of customers, the p-value is 0. And for the shift variable, especially for the not variable, the p-value is 0.351. Well, what we conclude, if you remember from our previous discussions, is that if p-value is less than the level of significance, we identified it as 0.05. Remember, it is 1 minus 0.95, right? And if the p-value is less than that alpha value, alpha in this case, again, 0.05, then we reject the null hypothesis that the variable is insignificant in the multiple linear regression equation. In our case, we reject the null hypothesis that variable is insignificant, meaning that variable is actually significant. So we go ahead and use them. In this case, we keep total employee hours in our equation, total number of customers in our equation, but the shift variable is has a p-value of 0.351, and it is greater than our alpha value, 0.05. We therefore go and take this out. What does this mean? This means that if you're calculating the overhead cost, the shift variable does not have enough statistical evidence to be significant in determining your overhead cost. Without even this information, you wouldn't really, know that by just looking at this data, you wouldn't even know whether your shift variable is statistically significant or not. That's one of the perks that you get from implementing multiple linear regression and looking at the ANOVA table. This is the ANOVA table, and then trying to see whether it has any impact on it or not. So variance inflation factors, VF values. These numbers are good as long as it is less than 5. We basically keep these variables in the equation. What does this tell us? It basically tells us how much, for example, the total employee hours has a VF value of 1.06. It means that the other variables are not really explaining this total employee hours that much. So this is good because it is basically telling us that there's not really a huge relationship between total employee hours and total number of customers and the shift information. Is this a problematic when we do have, is this a problematic thing if we have, for example, relationship of the predictor variables between each other? Yes, it does, because it creates a lot of noise and it makes things complex. And if the VIF value, for example, is greater than 5, some applications, if it is greater than 10, we start taking those variables with high VIF values out, because it is basically telling us that, one at a time, by the way, it's because VIF value indicates that some other variables, predictor variable in your problem is or are explaining the high VIF value predictor variable already, and it has nothing to do. Well, it has something to do with our problem, but it doesn't really add too much extra valuable information in multiple linear regression settings. Okay, so I'm going to take this shift out in a moment, but I want you to, well, this is the analysis of ANOVA table. It is, p-values are identical here, right? So what I want you to focus on here is the R-square value. R-square value overall, it is 87%, and it means that by using these information, total employee hours, total number of customers, and the shift information, my multiple linear regression can explain the 87% variance in the overhead information. So the changes that are happening in this overhead column, 87% of them can be explained by the variance in this column, can be explained by these three variables. So it is almost like a predictive power that we can relate to. But mathematically, it is just the percent of the variance that you can explain in this column by using these three variables. Okay, so adjusted R-square is less than that. It is 85.75%. This adjusted R-square value is going to be used when you play with these predictor variables. In a moment, I'm going to take this shift out, and then you will see that my R-square value is going to change, and my R-square value ultimately is going to change as well. But when we do play with those set of predictor variables, you take a look at the change in the R-square value, adjust R-square value instead of the R-square value overall. Because adjust R-square value is going to tell us whether it increased or decreased depending on the number of predictive variables that we use. Okay, so what else I have? I do have 4 different plots here. The first one is the parity plot. You see that Minitab gives you the standardized impact of different predictive variables here. So predictor A here is the total employee hours, predictor B is total number of customers, and predictor C is the shift. So it came up with this threshold value as of 2.04. And you see that A and B are good. They're exceeding this important threshold, but shift variable is not exceeding that. It has only 0.94 value. It is a good indication that shift variable is not really a determining variable when calculating the overhead cost. So this is the normality test for the residuals. So residual is basically what is our overhead cost right here versus the Minitab's predicted overhead value and the differences between them, right? So, and then we do have the residuals on the x-axis here on the first one, and then the percentile on the y-axis. This is literally the normality test. As you can see, all the dots are on this straight line almost, right? It passes the normality test, which is a good thing. And these are all, fitted versus the residuals. So the Minitab's calculated version of the overhead costs are here, and the residuals are on the y-axis. Residuals, again, the difference between the original overhead cost versus Minitab's calculated version of the overhead cost. As you can see, those are pretty random. So this is also a check that there is no bias in our example. And it is a pass for this test. So these are all useful information, but most important ones that you have here is this equation, right? Because we have 2 equations, because we do have one categorical variable that has 2 possible values that you can take. And it is important to be able to read these p-values. If your p-value is less than 0.05, the same here, it means that it is a significant predictor variable to include in your analysis, as in this case, shift value is not a good predictor variable, so we're going to take it out. All right, how do we take it out? So let's go back to the version that we can see both the data and the Minitab analysis. We go to basic statistics again. Regression, fitted regression model one more time. And I am going to not include shift here. And I'm going to run the same analysis. All right, in this case, I do have only one equation because I have no categorical variable in this example anymore. And I take a look at the VIF values, those are good. I take a look at my R-square variable. I think it was 87.01%, and it decreased down to 86.64. But check out the adjusted R-square variable, and then it is now 85.83%, and it was 85.79%. So adjusted R-square value increased, which suggests that the variable that I dropped just worked for me, right? It got rid of some noise from the data. Although my overall R-square value went down, my adjusted R-square value went up. So when you deal with multiple linear regression, and then if you try to avoid different sets of predictor variables, you look at the adjusted R-square value. So it's a good thing that it went up. Okay, and then check out then also variance here. Those are p-values are all 0. It means that those are good. I can keep this from this point forward, and then look at the Pareto chart, A and B, total number of Rs and total number of customers. Those are significant. Normality test is good, and the other tests look good. So what I can do with this, now I can predict for the future, right? So I do have these time periods here that I'm planning for the future. Let me copy these into Minitab. What Minitab is going to do, basically, it is going to run this equation. It simply is going to take the total employee hours and total number of customers into equation. Shift is no longer something that I should worry about. Or what I can do is I can run this equation in Excel as well. What I need to do is I need to copy this information. Let me see if I can paste it here. All right, so yeah, this is my regression equation. So it basically tells me that it is 39.97. I can calculate my overhead now. 39.97 plus 43.54 times my total employee hours. My total employee hours is going to be stored here, plus 0.6 times my total number of customers. Okay, there you go. So these are my overhead estimates by using multiple linear regression. So where did I get this equation again? I got it through multiple linear regression. If you were to do this analysis in Minitab, what you need to do is you copy this information, you paste them somewhere on the same worksheet in Minitab, okay? And now you go to regression, predict this time, because we already fitted a regression model. As you can see, it picks up my overhead as a response variable. It says enter individual values. It gives me the 2 predictor variables here. I already stored them in a column, so I'm going to come here and then say enter columns of values. And my total employee hours is going to be stored in the future employee hours, okay? And my total number of variables is going to be included, total number of customers, I'm sorry, is also future employee here. Future total number of customers. See what options we have. You're not going to touch that. Results. Prediction table is good. Regression equation is good. Let's hit OK. So it predicted, my future overhead cost by using this equation. What it does is it gives you multiple different tables when your input is the first one, for example. Future employee hours is this one, and then future total number of customers is 33, and it gives you the prediction fit. It gives you 95% confidence interval and prediction interval as well. And then it does it for the second one, and then the third one, and then the fourth one. It's too much information here. If you know the equation of the multiple linear regression, you could certainly use it in Excel by yourself, like I did. All right, thank you so much for your attention. This would be the end of the improvement phase.